Lecture 2, Inventory Control with Uncertain Demand, Section 1, Part 2. In this part, we will have the Newsvendor or Newsboy inventory model, and this is for a single period inventory model. And the single period could be a day, a week, a month, a season, or even a year, and it depends to the procurement periods. Also, yeah, usually we consider the shorter periods like a month or at most a season for the Newsvendor model, and we assume that we don't have the chance to reorder during the period because of the supply time period. So we will have just one order at the beginning of the period or sometime prior to the period, because of the lead time, but we will receive that order at the beginning of the period. So let's assume that this is our period here, single period, and we have ordered Q units, and we have it right at the beginning of the period in our inventory. Okay, then for the situation at the end of the period, we may have two situations. The selling process or demand could go like this, and as you see here, in this case, still we have time to the end of period, but we have no stock. So this is called stock out situation. So in this case, it's actually the case that Q is less than D, so it's actually underage case. Okay, underage case. So we will have some lost sales at the end of the period, or it could go like this, and at the end of the period we may have some inventory in our stock, but it's over. I mean, there is no chance to sell this item, so we'll have excess inventory in our stock at the end of the period. So this is for the case that the Q that we have ordered is greater than the D that we will have in this period, and this is called the overage case. Okay, so yeah, as you see here, for the inventory policy, at the end of the period, we may have one of these two costs, no, not both, one of these two costs. It could be an underage cost, or it could be an overage cost. Okay, and we show the unit cost for overage by CO and the unit cost for underage by a CU. Okay, and here we want to actually minimize the expected costs incurred at the end of the period, and we'll do this by optimizing the order quantity, I mean Q. Okay, so the assumptions here that we have for Newsvendor model, we assume that we have a single product, just one good, and we'll have a single period, and we will order our requirement at the time of the beginning of the period if there is no lead time. But if we do have lead time, then we need to order a time prior the beginning of the period. Okay, and we will use that order quantity to satisfy demand during the period. So we won't have reordering during the period. Okay, and all relevant costs can be determined on the basis of ending inventory. Yes, at the end of the period, if we have no items in stock and we had stock out situation prior, I mean sometimes prior ending the period, then we are in the underage case, and it will have a cost. Okay, but if at the end of the period we have some excess inventory in our stock, then it's the case of overage, and it will have a cost for us. So yeah, we can calculate the cost at the end of the period. And here we assume that demand is a non-negative random variable. So yeah, usually we can assume that the demand is normally distributed, normal distribution, but it could be other distributions, or it could be discrete as well. Okay, and in this model, I mean, the first model here we assume that there is no initial inventory in our stock. Okay. So let's see what's our approach to analyze this problem and obtain the optimal order quantity. So at first, in the first step, we need to formulate the cost function in terms of the random variable demand, and also our decision variable q. Okay, and then in step 2 we'll determine the expected value of the cost function, and then we need to minimize this expected value of the cost function. And in step 3 we'll obtain a value for q that minimizes the expected cost function. So this approach, I mean, this procedure will be the one that we will use for almost all of the uncertain inventory models in this chapter. Okay. So the first step, let's have the expression for the cost function. So here we define GQD, I mean, the cost function in terms of Q, our decision variable, and D as the random variable for demand. Okay, so Q will be the quantity that we are going to order at the beginning of the period, and D will be observed during the period. It's a random variable. So the GQD will be like this. So the first term is CO, the overage unit overage cost, times maximum between 0 and Q minus D. So in this case, if Q is greater than D, then the maximum between 0 and Q minus D will be Q minus D, right? Q minus D. Then in this case, we will have the overage case, and CO will be multiplied by Q minus D, right? But if Q is less than D, then the maximum between 0 and a negative number here will be 0, right? So yeah, this will be a negative number. So let's show this by number sign here. So, and it will be 0, right? So in this case, we have the underage case, not overage case. So this term will be 0, and we will go for the underage case here. In the underage case, again, it's exactly the same as the previous term. So if D is greater than Q, this means that Q is less than D, right? Then this term will be a positive term, and then by having that, the maximum will be that positive number, and so C will be multiplied by that positive number as the underage amount. But if D is less than Q, this term will be a negative number, and the maximum will be 0, right? So yeah, by this function, actually we have formulated the cost function for the Newsvendor model at the end of the single period. Okay. Now in step 2, we need to obtain the expected value of the cost function. We call this as GQ. So GQ is the expected value for the GQD. So to do so, we will consider the demand as X here. So X is a random variable. It has its PDF probability density function as fx. So if we take the integral over 0 to infinity on this term and also on this term, so by doing that, we will have the expected value of the cost function, right? And this can be easily converted to these terms. So the CO is in the case that Q is greater than D, right? So here will be 0 to Q, Q minus X times Fx. And the underage is the case that D is greater than Q. So D will be over Q to infinity, X minus Q times Fx ds. So this will be our actually expected value of the cost function at the end of the single period. Okay. So in step 3, we want to minimize the expected cost function, and to do so, we can take the first derivative of that expected function with respect to q. So if we do so, we will have these terms as you see here, and here this term, as you remember in your probability course, it's the definition of the CDF, right? The FQ. So we can replace that by FQ, so CO times FQ, and then minus CU, again, integral over Q to infinity of Fx dx will be 1 minus FQ, or the yeah, let me write here. This is the case that probability of, let's say, X be less than or equal to Q. So it will be FQ, right? And the second term, this one will be the probability of X being greater than or equal to Q. So it will be 1 minus FQ. Okay, so yeah, by replacing these terms, we'll have at the end this term. And in order to make sure that the expected cost function is convex and we can obtain the minimum point by setting that first derivative, this term by 0, so we will check the second derivative here, and as you see here, it's greater than or equal to 0 because CO, CU are non-negative numbers, FQ is a non-negative function, so in total it will be a non-negative term. So you can say yes, the GQ is a convex function. Then if we set this equation to be 0 and solve that for Q, as you see here, we will obtain this closed form function to obtain the Q star. So the Q star, I mean the optimal order quantity, can be obtained by this equation. FQ star should be equal to Cu over Co plus Cu. Okay. So we obtain this equation in order to calculate the Q star. So here FQ star is actually this. The probability that D is less than or equal to Q star, this is equal to Cu over Co plus Cu. So here, as you see here, we want actually to satisfy all demand during the period by the Q star, I mean our order quantity with this probability. So the Cu over Co plus Cu is called critical ratio here, and yes, it will determine the probability that we will be able to satisfy all demand during the period by ordering Q star. Okay. So for continuous demand distribution, that equation is solvable. So we will solve that equation to obtain the optimal Q. But if it's discrete, I mean this function is discrete, then we'll see how we should be obtained the Q. So we will see this in an example later in this part. But let's have a discussion here. What happens when the underage and the overage costs are the same? So in this case, CO over CO plus Cu will be 1 over 2 or 0.1. Okay, so this means that the probability of D be less than or equal to Q star should be 0.5. Okay, so if we assume that we have a normal distribution for the demand, and as you know, here is the mu, and the probability of d be less than or equal to mu, like in this area, is 0.5. So in this case, the q star, in this case, the q star will be exactly the mu, the mean. So yeah, if the CO equals CU, so it doesn't matter if we have overage or underage, the costs are the same, so it doesn't matter we are in the case of overage or underage. So in that case, we will order exactly the mean of the demand, the expected value of the demand, which is mu in the normal distribution. Okay, and for the discrete distribution, we'll have an example later in this part. Okay, let's have an example here. Here we have a product that the weekly demand is normally distributed with mu of 11.73 and a standard deviation of 4.74. Okay, and we assume that we have a single period, so it's somehow a fashion good or a food or perishable good, or and so on. So we are assuming the news vendor model here. The purchase price is 25 cents. Purchase price. The salvage cost, if we have excess inventory at the end of the period, we need to sell it as scrap for the salvage value of 10 cents, and the sale price here is 75 cents. So in order to solve this problem, at first we need to obtain the CO, the overage cost, and CU, the underage cost. Okay, so here the CO is the case that we have excess inventory. So if we have excess inventory, we will sell them as a scrap value of 10 cents. We have purchased them with 25 cents and we are selling them as 10 cents. So 25 minus 10 will be 15 cents as our overage cost, right? Yeah, here we have about 25 cents, but we are selling them as 10 cents, so we are losing 15 cents per unit, right? That's this overage cost. For the underage cost, CU here, as you see here, we are purchasing the goods per unit of 25 cents and we're selling them at 75 cents. So 75 minus 25, which is 50 cents here, we are making profit as 50 cents per unit. And if we face a stock out situation, so we are losing this profit, so the CU or underage cost becomes 50 cents. Okay, now we do have the CO and CU. So the equation for obtaining the Q star here is this: if Q star is CU over CU plus CO, right? So it will be 50 divided by 50 plus 15, so it becomes 0.77. So the FQ star is actually this: the probability of demand be less than or equal to Q star should be 0.77, and we know that the distribution is normal distribution. So here we need to convert this to standard normal distribution, right? So to do so, the P, let's show the standard normal by Z value here, Z variable. So the probability of Z be less than or equal to Q star minus mu over sigma should be 0.77. Okay, and as you know, again, this will be, let's say, the Z alpha value, and this is here, let's say, the alpha. So we can use the standard normal distribution table to obtain the Z alpha based on the alpha. So here the alpha is 0.77, and if we go to let's have the general formula here first, and then we'll obtain the value for Z alpha. So by having this, we'll say Q star minus mu over sigma should be equal to Z alpha, right? And then Q star will be mu plus Z alpha times sigma. So that's our general formula for normal distribution. And now if you go to the standard normal distribution table and consider alpha as 0.77, then the Z alpha will be here will be 0.74. Okay, 0.74. Now the Q star will be 11.73 plus 0.74 times sigma, which is 4.74. Then it becomes 15.24. And now we can round it up or down. It depends, to the situation. But since here in this example, let's assume that it's a newspaper case. So in this case, we need to have a full number, right? So here we will round it to the closest integer number, which here in this case is 15. So it will be 15 units at the end. Okay. Let's have another example for a discrete distribution here. So here we have a discrete distribution for demand, which is this, as you see here. So for any value for demand, we have its probability here. Okay. So so for any discrete distribution case, at first we should obtain the CDF function, the cumulative distribution function, or capital Fx. Okay, so here for the first one, the CDF will be equal to that probability, but for the second one, we need to add this value with this probability in order to have the value for the CDF, which is 0.2 here, and then 0.2 plus 0.4 will obtain 0.6, and then 0.6 plus 0.2 will obtain 0.8, and then 0.8 plus 0.1 obtains 0.9, and at the end 0.9 plus 0.10 will be 1 here. So that's our cumulative distribution function. Then we need to obtain the critical ratio. So in this example, we assume that we have the same financial data. So the critical ratio, which is Cu over Cu plus Co, here is 0.77. Okay, so by having the definition of that equation, we have Fq star equals 0.77, right? So here we do have the Fx function. So we'll see in what interval this number falls. Okay, so let's go here, and as you see here, 0.77 will be between these two numbers, right? 0.6 and 0.8. So in this case, we'll always obtain the upper limit of that range. So the upper limit here is 0.8, and it obtains the 15 as the order quantity, right? So yeah, so here Q star becomes 15. Okay, so this is how we solve the discrete probability case. Okay, thank you.